Okay, let's unpack this unbelievable premise right from the start. In the world of technology, when a paradigm dies, it typically stays dead.
Oh, absolutely.
I mean, think about our digital graveyard, right? You've got floppy diskettes, VHS tapes, cathode ray tubes.
Right.
They're charming relics for sure, but nobody expects them to crawl back from the grave to challenge, the latest tech.
And for decades, the analog computer was the textbook definition of obsolete. It was just monstrous, mechanically clunky, and notoriously difficult to program. And its biggest problem was, well, it just wasn't very precise.
So today we're deep diving into what's being called the unbelievable zombie comeback of this mid-20th century behemoth. And just to be clear, we're talking about machines that used continuous voltage or mechanical parts to solve problems, not the discrete zeros and ones that have defined, the last 50 years of computing?
Yeah. Precisely. And to understand this resurrection, we first have to fully appreciate the original demise. I mean, why did it die in the first place? The primary fatal flaws were really twofold: physical inflexibility and crippling accuracy limits.
Physical inflexibility, that just sounds like a nightmare for any modern programmer.
It was. If you wanted to change the function an old analog machine was performing, you couldn't just, upload new code. You had to physically reconfigure the hardware.
Wait, what does that mean in practice?
We're talking about shifting mechanical levers or physically plugging in different operational amplifiers and potentiometers to manually change the circuit itself. It was this very tangible, hands-on process that required, specialized knowledge and a huge amount of patience.
A completely manual reprogramming process. That sounds agonizingly slow compared to just hitting compile on a digital machine and instantly running a new simulation.
Agonizingly slow and agonizingly imprecise. Beyond the physical clunkiness, they had these huge accuracy issues that were rooted in just fundamental physics. The inputs, which were supplied as a continuous voltage or, pulse frequencies, they were just inherently error-prone. They were sensitive to ambient temperature fluctuations and subject to background electronic noise, which would just amplify error throughout the whole system's operation.
And what was the quantifiable limitation there?
Yeah.
Because we're so used to high digital precision now, sometimes tracking calculations to 16 or 32 decimal places.
Yeah, it's a different world. The precision of an analog computer readout was typically limited to just 3 or maybe 4 significant figures.
Wow.
So when you ran a long, complex function, the expected error grew really quickly. You'd be looking at an error around 10 to the -4 plus or -1.
So just to put that into context for you, our listener, that means your error is approximately 1 part in 10,000.
Right.
1 part in 10,000.
Yeah.
That's okay if you're measuring the temperature of your swimming pool, I guess, but not if you're trying to track a missile trajectory or design a complex bridge.
Exactly. Now, compare that to modern digital precision. Digital systems rely on discrete values, and they can implement these really robust error correction algorithms. They often achieve errors of approximately 10 to the -10 in some fields.
So 1 part in 10 billion?
1 part in 10 billion. And that massive inherent precision gap was the single most powerful factor that drove analog computation into obsolescence between, say, the 1950s and the 1970s.
Okay, so this is the core mystery we need to solve then. If analog is so fundamentally flawed in accuracy, why is every major tech player, IBM, Intel, the entire AI hardware startup ecosystem, pouring billions back into this architecture? Are they just deliberately choosing inaccuracy?
It's not that they're choosing inaccuracy, they're choosing a different trade-off. The resurrection isn't happening because the old tech suddenly got 10 times better at precision. It's happening because our dominant digital paradigm, the high-speed, high-precision one, has hit some fundamental physical roadblocks that make it unsustainable for what we need in the future, especially AI.
So the limitations of our amazing digital computers are actually creating a necessity for these old patient ideas to return, but updated and highly specialized.
That's our mission today. We're going to unpack those digital bottlenecks, specifically the architectural flaws and the energy catastrophe that follows from them. And we'll explore how modern analog and hybrid and even specialized optical architectures are solving these huge challenges in AI and scientific computation by prioritizing speed and energy efficiency over that brute force precision we've gotten so used to.
Right. So the question we're asking is, what can analog do well enough that digital can't afford to do at all anymore?
That's it, exactly.
Let's start with a bit of history then. Just understand what analog computing actually is and where its natural strengths lie, because it is just a fundamentally different approach to solving problems than the digital world we all live in.
That's crucial. When we talk about analog computers, or ACs, we're talking about machines that use continuous physical quantities, like electrical voltage or hydraulic pressure, or even mechanical movement to model and solve problems. The critical distinction here is that the physical structure of the computer itself is an analogon or an analogy of the system being studied.
You mean the arrangement of resistors and capacitors on a circuit board literally mimics the physics of a completely different system, like a car suspension or a weather pattern?
Precisely. I mean, if you trace the history, you see simple examples like the slide rule or nomograms, but it evolved into these incredibly complex mechanical devices that were used for real-time control.
Like what?
Well, things like naval gunfire control computers or the Norden bomb sight used during World War II, which was just a remarkable piece of mechanical analog engineering used to solve the dynamic equations you need for accurate bomb delivery.
So it sounds like the key insight here is that for certain types of physical problems, the math inherent in one physical system, say an electrical circuit, is identical to the math in another, say a bouncing spring.
Exactly. The mathematical similarity between components is it's really striking. A linear mechanical system uses components like springs, which store potential energy, and dashpots, which are these viscous fluid dampers that dissipate energy. They're all governed by differential equations.
Okay.
Well, an electrical circuit uses capacitors, which store electrical energy, and resistors, which dissipate it. They are described by equations of the exact same form.
So simulating a complex mechanical system like the dynamics of some specialized factory robot is really expensive and difficult to modify in the real world.
But building an electrical equivalent is much cheaper and much faster. Engineers would arrange operational amplifiers, potentiometers, and these linear components to form a circuit that followed the exact same differential equations, or ODEs, as the mechanical system. Then they could just change a coefficient instantly by twisting a knob on a potentiometer and see the resulting physical dynamics change on an oscilloscope.
And this inherent structural relationship is what gives analog computation its native strengths.
Absolutely. ACs are just ideally suited for real-time simulation and continuous data processing, particularly for systems described by these ordinary differential equations. Because the electrical system is a direct analogy to the physical system, it operates in continuous time, much like the physical world itself.
And the practical benefit goes beyond just cost and speed. What about the human element, the person using it?
Right. That's where the intimate control aspect comes in. The source material we looked at notes that experienced users of electronic analog computers often reported having a much more intimate control and understanding of the problem compared to early digital simulations.
Why is that?
Because they physically wired the problem, they gained an inherent, tangible intuition about the system's dynamics. They could literally touch the hardware and understand the physics.
That really reflects this theme we're seeing of people returning to more patient, hands-on technology. But, ultimately, intuition didn't win the day. Precision did.
Digital's dominance hinged entirely on its ability to offer unmatched versatility and machine-level precision, all by relying on discrete ones and zeros. When you solved a system of differential equations digitally, you weren't constrained by component noise or temperature. You could achieve that accuracy of 10 to the minus 10, which was sufficient for, well, virtually any scientific or engineering task.
And analog's inherent error ceiling of, 1 part in 10,000 meant it was simply left behind for any application demanding high accuracy, things like financial modeling, pure mathematics, or complex encryption.
It was the fatal flaw. Analog computers offered speed and intuition, but digital offered universality and accuracy. When the cost of digital computing started to fall, there was just no contest. Analog died.
But now, we have to look at what has changed about the digital world that makes that speed for low precision trade-off suddenly necessary again.
Well, what's changed is that the entire digital industry is running into a wall. A fundamental physical brick wall. For decades, Moore's law, the observation that we could double the number of transistors on a microchip every 2 years and thereby increase computer speeds and efficiency, was basically gospel.
The relentless drive toward miniaturization.
Exactly. But now, as transistor sizes approach fundamental physical limits, we're talking about components that are only a few atoms wide, that scaling is diminishing. We're being forced to look for completely new approaches to increase performance and, critically, to increase energy efficiency. We are hitting the thermal wall.
The thermal wall, meaning if we push any more electrons through this tiny space, the heat it generates becomes unmanageable and, well, destructive.
Correct. And compounding the scaling limit is the critical architectural flaw that's embedded in virtually all modern computing devices, the von Neumann architecture, which has been the foundation of digital design since the 1940s.
Okay, for you, our listener, who might not be familiar with that name, what exactly is the von Neumann architecture, and why is it a problem today?
It's a design principle that physically separates the central processing unit, the CPU, which does the calculation, from the memory where the data is stored. This was revolutionary 50 years ago because it made programming incredibly flexible. But today, it creates a massive bottleneck.
How does that separation cause a bottleneck?
To run any calculation, the CPU has to constantly fetch data from memory, bring it over to the CPU for processing, and then often send the result back to memory. This process of constantly shuttling data back and forth is the von Neumann bottleneck. And crucially, this data movement consumes a substantial amount of energy, and it significantly slows down processing speed, especially for the massive data-intensive workloads that define modern AI and large-scale simulations.
So it's a brilliant conceptual design, but architecturally, it's just really inefficient for big data. It's like having a top chef that's the CPU, but their kitchen is miles away from the pantry, the memory. Every time they need an ingredient, they have to run across town. The genius of the processor is completely constrained by the commute time.
That analogy perfectly captures the problem, and this commute, or data I/O, is what has led to an energy efficiency catastrophe in modern computing. We need to compare the energy consumption of conventional digital computing, where, cloud data centers and high-performance computing systems consume megawatts with the gold standard of efficient computation, biological intelligence.
Give us those numbers again, because they provide the ultimate context for why this analog comeback is so urgent.
Okay, so consider the human brain. It operates on a tiny power budget, only about 12 to 15 watts.
Like a dim light bulb.
Right. Yet it achieves an estimated energy efficiency of 3 times 10 to the 14 floating point operations per second per watt, or FLOPS per watt.
3 times 10 to the 14. That number is almost impossible to grasp. How does that compare to our best digital hardware?
Compare that to a state-of-the-art commercial digital processor from the early 2010s, which had an energy efficiency of only 5.88 times 10 to the 8 FLOPS per watt.
Wait. I just need to fully internalize that difference. We are talking about 6 orders of magnitude. The digital processor is at best 1/millionth as energy efficient as the biological brain.
A million times less efficient. This colossal gap is the driving force behind the analog comeback. If we could close even a fraction of that gap, it would revolutionize everything, from global energy consumption to what our cell phone batteries can do.
Think about the implications of that. If your phone operated at biological efficiency, the battery might last 6 months instead of 6 hours.
That's the scale of sustainability and performance difference we were trying to bridge.
So the central digital problem is this data movement bottleneck, which wastes huge amounts of energy. The elegant analog solution must be to eliminate that movement entirely. And that is where the concept of compute and memory redefines the technology.
Exactly. The core strength of the contemporary analog revival is the concept of performing computations directly inside the memory array, which is a profound shift away from the von Neumann model.
That seems like a massive architectural challenge. How does that work in practice with new chips being developed by companies like Mythic or IBM?
They use specialized non-volatile memory elements like tunable resistors or phase change memory, which is often abbreviated as PCM.
Can you define phase change memory for us?
Certainly. PCM is a type of memory element that stores data by changing its physical state, specifically its electrical resistance. These small components can be tuned very accurately. And crucially, in analog computing, these memory elements do double duty. They store the weights of a neural network, that's the memory, and they are the computational components themselves.
So instead of transferring a stored weight from memory across a bus to the CPU to be processed, the weight is the component that processes the input.
That's the innovation. Inputs are supplied as electrical voltages to this memory array. When the voltage passes through the network of tunable resistors, physical laws dictate that the currents naturally sum up, that's Kirchhoff's law, and the outputs are collected immediately as electrical currents. This completely eliminates the need for constant energy-consuming data shuttling between separate processing and memory units, striking right at the heart of the von Neumann bottleneck.
It sounds like a completely different paradigm, one that really mimics the brain, where processing and storage are intrinsically intertwined.
It is a massive step towards neuromorphic or brain-inspired computing. By eliminating that data movement, you get superior power efficiency and lower latency, which
Right.
is absolutely crucial for the high-volume, real-time demands of modern AI inference tasks. So if solving the von Neumann bottleneck provides the energy efficiency, the next major advantage of modern analog systems is just their sheer speed, and that's derived from what we call intrinsic parallelism.
We hear about parallelism all the time in digital computing. I mean, think of powerful GPUs with thousands of cores.
Yeah.
How is the analog version fundamentally different?
Digital parallelism usually means executing many discrete instructions at the same time, but it always involves communication overheads. Data needs to be synchronized, it needs to be routed, moved across a network or a chip fabric. Analog systems feature intrinsic parallelism. All the computing elements, whether they're processing voltages or currents, work simultaneously in a continuous time fashion because they are fundamentally connected through physical components.
Can you give us a concrete example of where this intrinsic parallelism really translates into a massive speed advantage beyond just AI?
Yeah, let's consider scientific computation, specifically solving time-dependent partial differential equations, or PDEs, which are essential for modeling everything from aerodynamics to weather. A digital architecture solves the problem by breaking space and time into a grid. When one element in the grid calculates its next step, it needs neighbor values from adjacent elements. Digital systems are constrained by communication overheads latency when obtaining those neighbor values across the grid. Time is literally lost waiting for data to be exchanged and synchronized.
Which again is the digital bottleneck just in a different guise.
Exactly. But in analog systems, communication between grid neighbors happens continuously through physical connections, the circuit wires, at the same time as the local circuit operation is running. And the critical outcome here is that no time is lost for communication. The computation and the communication are happening simultaneously.
That structural advantage must lead to colossal speedups in applications like computational fluid dynamics.
It does. For solving large coupled systems, analog computers exhibit what's called O of 1 runtime scaling. That means the time required for a solution doesn't grow nearly as quickly as the problem size increases compared to digital solvers. Researchers are predicting this could lead to potentially 1,000 times faster solution times compared to digital solvers for complex PDE models. So imagine cutting weather prediction time or the simulation of a new jet engine from hours down to just minutes. That kind of speed is transformational for R&D.
And we can see this efficiency in the core operations, too. I mean, the sheer physical resources required to perform basic math are dramatically lower in analog, which contributes massively to the energy savings.
Absolutely. Think about simple addition. In analog, you apply Kirchhoff's current law. Current entering a node must equal the current leaving it. So if you feed 3 different currents into a single wire junction, they sum up naturally. A single wire performs addition.
And what does that look like in the digital domain?
Well, to add 2 standard 8-bit digital integers, you need a circuit built of approximately 240 transistors, depending on the implementation.
240 transistors versus 1 wire. That is an astonishing difference for basic arithmetic. But that sounds too good to be true. I mean, if adding 2 8-bit integers digitally takes 240 transistors and analog takes 1 wire, what calculation are we losing access to? Where's the inevitable analog cost?
The cost is always accuracy and the ability to branch or apply complex logical operations. Digital addition is guaranteed to be 10 to the minus 10 accurate. Analog addition is subject to component noise and is only 10 to the minus 4 accurate. But for neural networks, that lower precision is often sufficient.
Let's look at multiplication then.
Multiplication is even more stark. Analog multiplication, using components like the Gilbert cell, which is a well-established circuit design, requires only 4 to 8 transistors.
4 to 8.
Now, if you want a maximum speed digital arithmetic unit to multiply 2 8-bit integers with guaranteed high precision, you could need as many as 3,000 transistors.
4 transistors versus 3,000. This is why analog computing holds such promise for massive parallelism with a significantly smaller power and area footprint. The fundamental units of computation are just radically simpler.
And that brings us back to the elephant in the room. Precision. The whole system is cheaper and faster because it is less precise. Does that negate all these incredible advantages?
It has to limit the application space severely. Analog is fundamentally not a general-purpose replacement for digital.
It dictates the sweet spot. Our quantitative studies show that the energy efficiency advantage of analog only exists for low-precision data. The crossover point where digital starts becoming more efficient again is typically around 8-bit or maybe 12-bit precision.
Why does pushing past that 8 or 12-bit limit become so exponentially expensive for analog?
It's the battle against thermal noise. To achieve high precision in an analog circuit, you need a very high signal-to-noise ratio. If you try to push for, say, 16-bit analog precision, the required area and power consumption just balloon. You have to increase the area and power by a factor of 256 compared to 8-bit just to effectively control that thermal noise and maintain the ratio. The cost just rapidly outweighs the digital alternative.
So low precision is cheap, fast, and highly efficient in analog. Why does that matter so much right now in 2024?
Because this low-precision sweet spot is absolutely perfect for the current demands of artificial intelligence, specifically deep neural network, or DNN, inference tasks.
We hear the terms training and inference a lot. Can you just clarify the distinction for us and why inference is the sweet spot?
Certainly. Training is the phase where you feed massive amounts of data to the neural network for days or weeks, allowing it to learn by adjusting the millions or billions of internal parameters, or weights. This process often requires very high precision, like 32-bit floating point, to make sure it converges and is accurate.
And inference.
Inference is the real-world deployment of that trained model. It's the moment the AI is actually classifying an image, or transcribing a voice command, or making a real-time decision in a self-driving car. Inference tasks, unlike the heavy training phase, can tolerate much lower resolution, often 4-bit or 8-bit. They require low power, have to be done quickly, so low latency, and they benefit immensely from intrinsic parallelism, especially when they're deployed on compact battery-operated devices far from a cloud data center.
So training still requires massive digital high-precision power, but once the model is trained, the low-precision, high-speed analog chip is the perfect vehicle for its deployment.
Exactly, and this realization is fueling a massive market shift. Market reports indicate the analog AI chip market is experiencing rapid expansion, with an estimated compound annual growth rate, or CAGR, of over 35% projected over the next decade.
That is just explosive growth for a seemingly dead technology. Where exactly is this market activity concentrated?
It is heavily driven by edge AI and Internet of Things, or IoT, devices, things like smart cameras, low-power health monitors, industrial sensors. These IoT devices are projected to account for over 65% of the total analog AI chip market by 2030.
The need for localized, low-latency intelligence in billions of compact battery-operated applications is a perfect match for analog's core strength, his speed and efficiency over raw precision.
And that's why companies like IBM, Intel, Mythic, and BrainChip are already heavily invested. They recognize that digital systems simply cannot deliver the required energy efficiency for this volume of small distributed compute nodes.
It's becoming really clear that the future isn't purely analog, nor is it purely digital. It has to be a marriage of the two, using the strengths of each to solve the problems that neither can manage alone. And this leads us directly to the concept of hybrid systems.
Hybrid analog-digital coprocessing is widely recognized as the most practical modern solution. We combine the continuous speed and efficiency of the analog accelerator with the precision, control, and versatility of the digital processor.
How do you practically integrate these two opposing computational approaches, one continuous, one discrete, without losing all those efficiency gains?
Well, let's start with a problem that plagued old analog computers: limited dynamic range. If a voltage representing a variable got too high, it would overload or clamp because the physical component just couldn't handle the magnitude. Modern proposals solve this using what are called hybrid integrators.
How does that work in a modern system?
The analog component is engineered to operate continuously within its safest, most stable operating range. If a variable starts to approach an overflow limit, the digital component takes over. It processes that analog range overflow digitally, effectively extending the dynamic range far beyond the physical limits of the analog components.
I see.
So digital acts as a smart safety net and a precision buffer, constantly monitoring and refining the analog output.
So digital manages the extremes, allowing the analog circuit to run freely and efficiently right in the middle. I know one of the most exciting applications is how this hybrid approach solves a problem that digital systems running traditional iterative algorithms really struggle with: complex scientific simulation.
Right. That brings us to the scientific co-processing model, where the analog accelerator provides the crucial initial guess, or seeding, for large, complex, nonlinear systems of equations.
And why are these systems so difficult for standard digital computers?
Okay, take partial differential equations, or PDEs, which are common in problems like modeling fluid dynamics, the Navier-Stokes equations, or complex heat transfer. Digital methods solve these iteratively. They make a guess, check the error, refine the guess, and repeat until the error is minimized. They struggle immensely with two issues: selecting reliable initial conditions and choosing the correct step sizes in their iterative process. If the initial guess is poor, the digital algorithm might take an agonizingly long time to converge, hours or even days, or worse, it might just diverge entirely and fail.
And this is where the continuous analog approach becomes invaluable.
It is the perfect task for analog's continuous time nature. The analog accelerator can run a continuous algorithm, like the continuous Newton method. Since this method runs in continuous time, the analog circuit always has an up-to-date evaluation of the function. We completely eliminate the digital problem of having to select an optimal, discrete step size. This makes the analog convergence process far simpler, faster, and much less sensitive to a poor starting point.
So the analog accelerator quickly finds a reliable, low-precision approximation of the final solution, the analog seed. Then the digital system steps in.
Correct. The digital processor, usually a high-precision GPU or CPU, takes this reliable analog seed and then only needs a few final high-precision steps to refine it. This drastically reduces the total number of iterations the digital system needs to perform.
Can you quantify the benefit of this analog seeding?
Certainly. In one significant study using a GPU-based solver for the 2D Burgers equation, the simple act of using analog seeding decreased the overall digital solution time by 5.7 times and the energy consumption by an astounding 11.6 times.
Wow.
And crucially, the time and energy spent in the analog step were negligible compared to the massive savings gained in the digital solver's operation.
That is incredible. A
Mhm.
5.7x speedup and 11.6x energy saving just because a continuous time analog circuit could reliably jumpstart a difficult digital process. This translates directly to reduced cloud costs, faster R&D cycles, and a lower environmental impact for industrial simulations.
It shows that analog doesn't have to replace digital to be revolutionary, it just has to solve the bottlenecks that digital created. But we still have that nagging fundamental problem: analog imprecision due to physical component fluctuation. Can that be fully mitigated in these modern chips?
Yeah, it's a critical question. You pointed out that traditional analog circuits rely on intrinsic physical quantities, like resistance or voltage, which fluctuate with temperature or repeated use, and that's the historical source of low precision. So how do they overcome that fluctuation in the 21st century?
This is where the cutting-edge research becomes really interesting. Instead of trying to perfect volatile physical device parameters, new research is shifting reliance to the inherently stable geometric ratio of transistors. They're making the computation dependent on the stable, lithographically defined geometric features of the devices, rather than the fluctuating electrical resistance.
That sounds like making the geometry of the chip itself the fixed, reliable constant.
Exactly. And this results in what's being called ultra-high precision analog computing. Using this geometry-based analog in-memory computing approach, researchers have achieved the highest reported precision for fully parallel analog operations, with a root mean square error as low as 0.101%.
That's a dramatic improvement over the historical 1 part in 10,000 limit. And the stability.
Crucially, this high precision was maintained even under extreme environmental conditions, from a deep freeze of negative 78.5 degrees Celsius up to a scorching 180 degrees Celsius.
Wow.
This stability is revolutionary. It means these chips can be deployed in harsh industrial or automotive environments where temperature swings would typically destroy analog fidelity.
Okay, and in the AI domain, you said noise is the primary limitation. How are they tackling that?
Additionally, in AI, advanced architectures are combating this using a technique called redundant coding.
Redundant coding. It sounds like a quality control mechanism.
It is. It just means repeating the same calculation multiple times and then averaging the result. This simple technique allows for programmable precision within a single network. You don't need high precision everywhere. You can dynamically allocate higher precision, so run more redundant coding only for the layers of a neural network, like ResNet 50 or BERT, that are known to be sensitive to noise, while running the other, less sensitive layers at lower precision for maximum efficiency.
So you don't waste energy aiming for high precision across the entire chip. You target precision only where the math actually demands it.
And this optimization technique, using dynamic precision, has been shown to reduce the energy consumption within a single AI model by anywhere from 43% to 96%. It's a huge driver of the efficiency gains we're seeing, allowing the architecture to adapt to the inherent needs of the algorithm being run.
Now, let's step beyond electronics entirely for a second. The efficiency goal is so pressing, and the digital limitations are so stark, that researchers are exploring analog computation in completely different physical domains. We're talking about light and chemistry.
This really highlights the desperate search for solutions beyond silicon. A company called Acatonics, for instance, is developing all optical processors. This is a next-generation architecture that uses photons, or light, instead of electrons for computation. The goal is to perform optical digital, optical analog, specifically for vector by matrix multiplication, which is the core operation of neural networks, and potentially optical quantum computing, all in a single chip.
Using light just seems like a natural way to solve the speed and bandwidth crisis, given how fast light moves.
It is. The key advantages include operating in the terahertz domain, which vastly exceeds the gigahertz clock speeds you find in electronics. Moreover, they can scale bandwidth extremely economically through a technique called multiplexing, allowing petabits of data to move through a single fiber. And crucially, the data signal itself never needs to be converted back into the electronic domain for processing. It eliminates conversion latency and power consumption. The data flows and remains optical throughout the entire computation.
And the other frontier is biochemical, computing inside cells.
That's PNNL's ChemComp project, which is exploring using chemical reaction networks to solve differential equations. The underlying premise is simple but profound. Cells naturally optimize reactions using minimal energy. When cells are running metabolic processes, they're essentially solving optimization problems extremely efficiently.
And the ultimate goal there is the creation of incredibly efficient biocompatible computers.
Exactly. One potential future application is the development of smart drugs or biological sensors that can detect a disease within the body and then autonomously respond by synthesizing and delivering therapeutics on demand. These unconventional architectures just demonstrate how far the quest for those 6 orders of magnitude of energy efficiency is pushing the boundaries of what we even consider a computer. As we conclude the technical discussion, it's really vital to reiterate the strategic role of this comeback for you, the listener. Analog accelerators are not and will not be general-purpose replacements for your CPU or your GPU.
They are specialized tools for specific high-value tasks where digital systems just fail miserably.
Precisely. They are domain-specific accelerators targeting classes of problems that digital systems struggle with because of the von Neumann data bottleneck and their high-power requirements. Those problems include high-speed scientific computation, complex nonlinear algebra, and, most prominently, high-speed, low-power AI inference at the edge.
It's a focused resurrection. And the comeback isn't just happening in major R&D labs like IBM or PNNL. There's also a return to this technology for education and hands-on learning, which speaks directly to that historical benefit of intimate control and understanding that analog systems offered.
And this brings us to the accessibility piece and the theme of patient technology. Initiatives like the Analog Thing, that are making high-quality, open-source analog computers available at low, not-for-profit costs, they're offering a return to tangible, focused tech exploration.
This isn't just nostalgia then. It's a practical learning tool. What kind of problems does a modern low-cost analog computer allow students or hobbyists to model?
It's a portable system that's designed for modeling dynamic systems. So think about complex interlinked processes like population dynamics or fluctuations in market economies, chemical reactions, or modeling the dynamics of mechanical feedback loops in control engineering. The programming process involves physically connecting patch cords and setting coefficients with rotary knobs. It's intrinsically interactive, experimental, and visual.
So the physical act of wiring the problem helps you internalize the mathematical model. You are physically manipulating the differential equations.
It fosters what they call collateral learning. By engaging in this hands-on experimental modeling approach, users gain a practical introduction to fundamental concepts in differential and integral calculus, as well as control engineering. It provides a tangible, intuitive link between complex mathematical theory and engineering practice that just typing code into a digital solver can't replicate. It's a return to patient tech, where you're forced to slow down and truly understand the system you're modeling.
So what does this all mean for the future of computation? The analog computer, the relic of the mid-20th century, is back because the 21st century has an efficiency crisis.
That's the summary of our deep dive. Analog computing's resurrection is powered by its ability to address the twin crises of the digital age. the crippling von Neumann data bottleneck, and the escalating power consumption of AI. It excels where low precision, high speed, and continuous time parallelism are paramount, solving problems that digital systems are simply too slow or too power hungry to handle effectively or sustainably.
So you now have the necessary framework to understand why major industry players, from IBM and Intel to specialized startups like Mythic and and even academic research groups, are heavily betting on this old technology. They're fundamentally transforming the future of edge AI, high-performance scientific modeling, and even technical education.
But let's leave you with one final thought, rooted in that incredible 6 orders of magnitude energy gap we discussed earlier between silicon and biology. This modern analog resurgence is heavily focused on neuromorphic and bio-inspired computing.
Right, we mentioned companies like Synsense, whose work is dedicated to low-powered chips designed for always-on healthcare and surveillance applications. They are chasing biological efficiency.
Right. The goal is clear. Close that massive energy gap. If this definitive convergence of analog speed, digital precision, and eventually the exotic capabilities of optical and biochemical methods succeeds, we have to ask, are we witnessing the final architectural leap that will finally allow AI to solve the truly grand challenges, like fully accurate real-time climate modeling, or even achieving human-level intelligence, all within a sustainable, low-power envelope, moving away from the energy-hungry digital architectures that currently dominate the field?
It's a compelling and potentially world-changing future to consider.